The next talk is on payment security using PKI by Mr. Mitesh Radia, Senior Manager NPCI. Mr. Mitesh Radia has done his BE from Electronics and Communication Engineering. He has worked with the software development for ATMs, that is automatic teller machines. He is currently working with NPCI for product development. Over to you, sir.
Hello everyone. We have seen a lot of presentations on what PKI do in the future. I would like to discuss what currently we are doing with PKI and how it is helping our payments to be secured. So the idea is to discuss how can we ensure that our current transactions are secure. Future is which is coming, we surely need to work on that. But what we are currently doing, are we doing it correctly? Are we doing it the way it needs to be? And are we ensuring that the regulations or the patterns which are put forward for the security are correctly in place? I'll start with a short introduction. Please bear with me if it has already been covered in some of the sessions in parts, but this background will be helpful to show you 3 examples where I am trying to show you how the EMV chip data is kind of secured using your PKI. There is something which is coming called as electronic toll collection. So when the vehicle passes by the toll plaza, the toll is collected automatically without even stopping. Even that product is coming out with the PKI infrastructure to secure your transactions. So this is where we need to have a short background, and then we'll look into the architecture, how this is actually covered. I'm assuming 2 things here, or basic thing that I'm assuming and what we are not debating on today is security is required for all payment transaction. No one has come and denied that security won't be required. But everyone has discussed what PKI is. I want to highlight something, what PKI is not limited to, or with PKI only we cannot achieve everything. PKI is not solution for all the security problems. What we are going to discuss here is PKI is very important for your security solutions, but still you need to have your vulnerability scannings, still you need to have your secure coding methods to ensure that your entire system is secure. PKI is very reliable, but the reliability goes out if it is being used as what this is not supposed to be. So if you are trying to use PKI using some ad hoc manner, using our algorithms, it won't be secure. It's proved that it won't be secure. We should never try and invent something. There are already standard algorithms which are available for PKI. We can use those algorithms. And why we need to use those algorithms, we'll see it in the further slides. Coming down to the basics, building blocks of security. We usually say that we want to hide some data, that is security. That is not what it is today. Only hiding data is not security. We want to ensure that the data, when it is sent from one system to another system, is not changed in between. If it is changed, we are aware when it is changed. So starting with the building blocks, we are showing here 2 parts of any shipper algorithms. There is a key which passes through an encryption block. There is a key which is used, the same key is used for decryption. These kinds of algorithms we call it symmetric algorithms. Now the best part in this is the algorithm for the encryption and decryption is known to everyone. It is not hidden. What is hidden is only the key. Since we are discussing PKI, for PKI, there exists a key pair. So in the PKI encryption standards, there are three things that we are using: a key pair generator, an encryption block, and a decryption block. The algorithms for the encryption and decryption are again open. Everyone knows those algorithms. Only the private key or the secret key is kept secret in the key pair. You can see here the encryption works with the message M. It goes through an encryption algorithm. What you get is a encrypted text or ciphertext. The ciphertext is fed to a decryption algorithm, and the decryption is happened using the secret key. Now, there is a question, how is this possible? Now, there are various without going into the technicalities, there are various functions like trapdoor functions, Diffie-Hellman algorithms, which we can use to perform the security, or which we can use to perform the encryption, decryption, key exchanges that we are going to see, the examples that we are going to see in the next slides. One more point on the trapdoor functions. What are actually trapdoor functions, which is very essential to understand. I'll be showing you some of the attacks in the end. These attacks are possible only because the PKI or the RSA is not used correctly. So in order to understand what the trapdoor functions are, these are basically one-way functions which can only be reversed using the secret key. So if you use the public key, the evaluation is very easy to compute. The computation part is very easy. The reverse of that is not possible without the secret key. So if you try to reverse it without the secret key, it becomes a kind of hard problem to do so with the computers. Now, the biggest problem that we were talking about using CAs, the key management, the public key sharing, and the hierarchy that happens with the public key, there is always a problem. Actually, the birth of PKI happened with the key management problem. If I want to keep something, or if I want to keep something secret, I can do it with a lot of symmetric algorithms. But the problem is sharing the secret key. And that always happens. If everyone wants to talk, A, B, C, D wants to talk with each other, each of them will have to share each of other's secret key with each other, which becomes like a problem like there are n members and there are n keys which are supposed to be shared. Obviously, this is not practical. We cannot share all the secret keys, and if one can share the secret key, there is no need of passing the secret key, just pass on the message secretly. Can we do it without trusted third parties? One way to share it is using the trusted third parties. So there can be a trusted third party which can be trusted by all the four parties A, B, C, and D, and everyone can share his own secret key with the trusted third party. Every system will have just one key. That is very, very feasible. But can we do it without trusted third parties? The answer is yes. And there are 3-4 ways, or there are many more ways. I have just listed 3 here. There is Merkle, Diffie-Hellman, and RSA. We'll be looking more into the RSA part because that's what's being used today. Slowly, we'll be moving to ESA, elliptic curve cryptography in the future, and I'll show you one example of that. So what is basically that we do in our communications when we want to communicate from one system to another system? There are so many systems in the banking world. Say, for instance, there is a system NACH that works with NPCI, and it is connected to various banks. There are various check clearing systems that are working. We need to pass the data through an encrypted channel so that no one can come in between and change the data or look at the data and understand what is passing through that channel. Now, I have shown you just a simple example here, but this example has a flaw. Any man in the middle can change the data and break the security. There are ways to solve it out, but this is the basic building block for that. So there are 2 parties, A and B. Party A shares the secret key with the party B. The party B uses the secret key to encrypt a random number, let's call X, and pass on that random number to party A. Now, party A can decrypt that random number because he has got the secret key. So public key is shared and the secret key is used to decrypt the data. And now that random number which is generated will be used to encrypt all the session messages. As I said, it is vulnerable to man-in-the-middle attack. I do not say this is secure for man-in-the-middle attack, but any eavesdropper won't be able to get your messages out of it. This was one part of channel security, where your channel or the transport layer, where the messages are passing between two systems, are secured. We have also discussed about the digital signatures. So along with the channel security, we also want to ensure that your files which are passing by from system 1 to system 2, your messages which are passing from one system to another system, should also be ensured that they do not come from an untrusted source. Should also be ensured that they are not modified in the way, in your passage of the message. And we add the signatures on it. Now, what is the benefit of using these signatures? These signatures are not only used on your strong PCs or servers. We can use these signatures. We are using these signatures on your, say, credit card chips, EMV chips. We are using these signatures on your basic authentications with Aadhaar, which we have just seen. So the importance of the signature comes from the processing power, which can also be integrated in your chip. Ideally, the signing part is easy, and the verification part, which is done, is using a strong system. But nowadays, the crypto systems have evolved, and even your chips can do both the parts. I'll slowly take you through the signature process. It is a bit different than encryption. In case of signatures, the secret key is used to sign the message. In case of encryption, the public key is used to encrypt the message. In case of signature, the secret key is used to sign the message. I think we have already seen the signature detail, where the secret key is used to sign, encrypt basically the hash of the message. So we calculate a hash of the message and we use the secret key to encrypt that. That's what the output what we got is called signature actually. In order to verify the signature, we need all the three data: the signature, the clear message, and the public key. So basically, any entity can sign the message which is having the secret key, and any entity with the public key can verify whether its message is coming from a trusted source or not. We will see more sessions on certificates also. We have seen one session from Radia BT on certificates. I just wanted to put down one part on X509 certificate formats, and there are other certificates formats also available in the market. So EMV is using its own custom certificate formats. When we look at the certificate format, the important part is we'll be using this information in next couple of slides, where we'll explain how the security is managed for the toll plaza and managed for the EMV chips. It contains various attributes, as we already know. It contains version information, which says what is the format of the certificate. It can be X509 version 1, version 2, version 3. Serial number, which is unique for a CA. Algorithm identifier, what are the algorithms we use to sign the certificate. Issuer name of the CA. There are other attributes which are also important for the certificates. And something important is, if an entity A trusts a certificate, if an entity A trusts a certificate with CA1, entity B trusts a certificate with CA2, can they both of them trust each other? There is a hierarchy which can be maintained, and yes, they can trust each other. There are other things which we need to take care of about certificate revocations. So when the private keys are compromised or the secret keys are compromised, we need to revocate the certificates. We need to call back those certificates. So every CA has to keep that list. This is where I wanted to discuss a bit about the static data authentication using EMV. So as you are aware, there are various EMV chips available on the cars. Now RBI has made it mandatory to use the chips. I think on the ATMs it will go out in a year's time. The EMV transactions will go out in a year's time. How are we securing, or how are we authenticating that whatever chips we are using is the correct chip? My card is not cloned. So if you use just the magnetic stripes of your card, using the magnetic stripe, it can be cloned very easily. and you can perform your transactions, and the real owner will not be able to know until and unless he gets an SMS or a statement. But using this PKI technology, we will be able to identify at that instance itself whether the transaction is genuine or a fake, whether the card is genuine or a cloned one. I've used a basic static data authentication technique here, and I'll then give you an example of bit higher version of this. So what happens is, in the IC card, in the chip card, in the payments world, there are issuers, acquirers, and you can say a clearing house. Issuer is the one who issues the card to the customer. Acquirer is the one who acquires the transaction. So issuer generates its key pair, the secret key and the public key. There is some data which is written on the chip. The chip will have some memory area, some specific data which is written on the chip is signed using the issuer's private key. This signed data, after the signature which comes out, goes into the chip. The public key which is of the issuer is signed by a CA. Say NPCI acts as a CA here. Is signed by NPCI, and the signed public key also goes on the chip. So what does your ATMs or what does your POS terminal have? The POS terminal only has the public key of the CA, that is NPCI here. When you go and perform your transactions on your POS terminals, when you go and perform your transactions on the ATMs, as soon as you dip your card, the chip data is read, and using the NPCI's public key, the issuer public certificate is trusted first. The first trust mechanism is issuer public certificate. If it is a valid issuer public certificate, nothing has been changed on the certificate, then using that public key of the issuer, the static data is trusted. So the idea is, when you look at this entire diagram, you will be able to see that just one public key is residing on the terminal. Using the single public key, you are able to verify the chips of all the different banks. Now this has a flaw, this technique has a flaw. You can copy the entire chip data, you can copy the entire certificates, you can copy the entire signed data, you can copy it entirely into a different chip, and it will still work. So cloning has not been stopped in that, or the skimming of the cars have not been stopped in that. What we have done to overcome this is, every transaction should be unique, and then only you will be able to stop the cloning of it. So since that is not the part of the PKI, I was not willing to put it in this. Every card which comes with its own key pair, every issuer will have its own key pair, and for every transaction a random number is generated, which is encrypted and sent to the terminal, and later the terminal or the ATM verifies that every random number. So using the EMV chip, every transaction that you do on your terminals, POS terminals or ATMs, every transaction is unique. Even though you do the same transaction twice, even though you withdraw 1,000 rupees twice, every transaction is unique. I'd like to give you one more example before we talk on some of the attacks of using the PKI crypto system, because they were not used correctly. If you look at this, the second example that I wanted to highlight is about the securing your toll transactions. So government is coming out with an initiative where every vehicle will be affixed with an RFID tag. And if you look at the RFID, this is an RFID, passive RFID tag, so it doesn't have any power source of its own. So what it does is, it takes the power from the radio waves which are coming from the antenna of the reader or the transmitter, and then it powers using those radio waves, and it backscatters the responses back to the reader. How do we make it secure? It is very easy to clone, or basically it is very easy to clone a passive tag. There are two reasons for this. In your EMV transactions, the chip which is there on your EMV card can do a lot of nice processing. But the chip which is there on your passive RFID tag cannot do any processing. And the reason is, It doesn't have any power source of its own, so it cannot have more than 8 to 10,000 logic gates, which restricts it to do any sophisticated processing, any crypto processing. So it's a dump memory. In this memory, the best part is there is an area which is, or there is a memory block which is written by the RFID chip manufacturers, which cannot be changed or which cannot be copied from one tag to or one chip to another chip, which is unique for that chip. It is like your MAC address of your network card. So what we have done is, again we have created two pairs of keys, one for issuers and one for NPCI, or one for the clearinghouse if you call it. The first pair of key that is from the issuer is used to sign this data which is there on the transducer ID. We call it transducer ID, which is constant, which is fixed, which cannot be copied, which cannot be cloned, because once written it is locked. And as soon as the data is signed, the signed data is written onto the tag. The public key which is there. Now, if you look at the tag here, the tag size is very small. If you use your normal RSA algorithms to sign the data, the signature footprint is too big. Here, the memory that is available is only in bits, 512 bits. It doesn't even go in some few KBs. So we have used here elliptical curve cryptography to sign the data, and the signature's footprint is very small. The security standards which are available are still equivalent to RSA standards using say 3072 modulo, using the key size of 3072, you can say that approximately. The signed data is written onto the chip. The issuer's public key and the NPCI's or the CA's public key goes to the reader or the toll plaza. So as soon as your vehicle passes through the toll plaza will read the memory banks of the tag. It will verify the keys first. There is a key index which is written on the tag. It will, using that key index, it is verified that is it signed using a correct key or not. Once the key is verified, it will verify the data which is written on the tag, it is changed or not. So these are the two simple applications. So we are already aware that the network is secured using the PKI infrastructure. We are already aware that digital signatures working. These are the two new fields which are overcoming the uses of cloning, which are ensuring that your transactions are secured in today's world. I would like to highlight some of the points. We talked about a lot of security using PKI, but I could tell you that if it is not used correctly, if it is not used, like I gave an example, if you create, everyone knows the algorithms, how to encrypt and how to decrypt, it is publicly available. If I write my own algorithm, it might not be secure. And the reasons why it is in be secure, there are some of the attacks which has been done. One of the attack is the timing attack. So if we use the, I have given you examples here in case of RRA because it is what is being used today in case of networks, very widely being used in case of network. The timing for encryption in RSA, so if you do your encryption in RSA, the timing for that is much less than the timing for decryption. And in case if you using the decryption time, so if some attacker uses the decryption time to verify it, what will happen is he will be able to identify the keys, the secret keys, which will make it difficult for the user. Just a minute. Yeah. The next attack, this is last slide basically. The next attack which I want to highlight is the power attack, and which happens mostly in your chip cards, in your credit cards, in your debit card which uses chip. And I gave you an example of SDA. To overcome the cloning, DDA has been implemented. There is still one more attack in the DDA. DDA saves you from cloning of the cards, but it doesn't save you from this power attack. What happens is, at the time of decryption, the chip uses more power. And looking at the power patterns, one is able to identify what the key is. So when you look at 1 million power patterns, 1 million decryption patterns, you will be able to identify what the secret key is, which is dangerous. So they have come with another algorithm which is called CDA. Without going into technicalities, I'll come back to another attack, which is faults attack, and which is very common, and it can be very easily overcome. So while implementing our security solutions, we should take care of all these things. That's the motive here. If we try to do decryption using the public private key cryptography, public secret key cryptography, and for some reason the decryption part is not correct, the adversary or the attacker will be able to understand what the secret key is. So instead of giving the output directly, we should always check, before giving the decryption output, we should always check whether that output is correct or not. So calculation time or the checking time for the output is really very less. It's like 10% of the total decryption time. So I understand the 10% of the time increases, but it's much better than to secure your system and then to make it open or vulnerable to the attacker. One note of caution here, which is the last point. To speed up the RSA decryption, there are many systems which what they have done is they have reduced the key size of the secret key, which should never be done. If you reduce the key size of your secret key, basically what will happen is it will make your entire security vulnerable. It is very easy to break the system. So we should not decrease the key size to speed up your crypto systems. So that is all from my side. Thank you.